As an introduction to our next session, 4.7, inverse trigonometric functions, I just want to quickly review what is an inverse function, and just so that that's going to give us some context for when we go into our trig functions. And let's just recall that if you look at this quadratic right here, y equals x squared, this does not have an inverse, as I wrote down right here, and that's because it's not one-to-one. Now, how do you tell if something is one-to-one? You can tell if something is one-to-one or not if you do the horizontal line test. So if I were to do a horizontal line test right here, as you can see, our parabola crosses this line 2 times, which makes it a non-inverse function. So in order to have an inverse, it has to pass the horizontal line test. Okay, and the horizontal line test is called one-to-one. So this quadratic f of x does not have an inverse. Okay, but what if we restricted this parabola? Meaning, what if we only graph part of it? Maybe then that could be one-to-one. And what I mean by that, let's just graph from 0 to infinity. So if I started at 0 and graphed it like this, wouldn't that be an inverse? Or I'm sorry, wouldn't this have an inverse now? So this is my new function, g of x equals x squared. However, my restrictions are for only when x is greater than or equal to 0, right? We're starting at 0, and then it goes on forever right here. So my point that I'm making right now is that my function f of x does not have an inverse because it's not one-to-one, but my function g of x is invertible, or it does have an inverse because it passes the horizontal line test. It's one-to-one. Okay, and let's just remember, like, how do we graph an inverse? Okay, so so since this is a quadratic, we know that the points here, if I plug in 1, I get 1, correct? If I plug in 2, 2 squared is 4, and if I plug in 3, 3 squared is 9. So if you remember, the way that you find the inverse points is you just switch x and y. So if I switch 1 and 1, well, that's just 1 and 1. Switch meaning the 1 goes here and the 1 goes there. Okay, so switch 2 and 4. So 4, 2, and switch 3 and 9. So 9 and 3. So basically, these points are our inverse points. So let's just graph those just to see what this looks like. 1, 1. This is just going to be a sketch here. Over 4, 1, 2, 3, 4, up 2, and 9, 3. 9, and then 3. Okay, so if I sketch this right here, hey, not bad. Let's remember that you know that you have an inverse, or one of the really neat properties of an inverse is that if you draw the line y equals x, and I'm going to say that this line right here is y equals x. If you draw the line y equals x, it should be, or you should have a reflection. Okay, and that's why when you switch the points, so if this is the point right here, 4, 2, then this point right here would be the point 2, 4. You see? Okay, so if you know what the original function is, you can find the inverse by just switching the coordinate points. Okay, and also if you don't have an inverse, you can restrict it. Now I needed to review all those properties because now we're going to dive into inverse trig functions. So we're going to use all these same properties, but now I'm doing this with trig. So let's just start with our sine function and see what the inverse looks like. Okay, so you might want to pause it here and just copy this down, and then as I explain this then. Okay, so the gray curve is our sine curve, and obviously it is not a function. I'm sorry, it's not one-to-one. Why? Because if I draw a horizontal line test, maybe if we just use the x-axis, it crosses it once, twice, 3 times, so it's not invertible. However, as I stated right here, if you go from negative pi over 2, and if you stop at pi over 2, which is the black part of our sine curve, this right here is invertible, meaning that this does, from the interval negative pi over 2 to pi over 2, this does have an inverse. Okay, And that's going to be very important to us. So it's the same thing like we did with the quadratic when we restricted it. We're going to restrict our sign to go from negative pi over 2 to pi over 2. So let's write down those domains. So the domain of our restricted sine curve, okay, is from negative pi over 2 to pi over 2. And the restricted range, let's see, it goes from -1 and it goes up to 1. So from -1 to 1. Okay, so what does the inverse look like? Okay, and so notice the notation that we're using, right? And when we learned this in chapter 1, if this was our function, the way that we notated the inverse is we went like this, right? And this does not mean f to the power of -1. This is just the notation of the inverse of f. So we're going to do the same thing here, is that this is called the inverse of sine. And another way of writing the inverse of sine is arc sine of x. These two are equivalent. So you can write the inverse of sine with the power of -1, or you can write arc sine of x. Both of these are different, and I'll explain where the arc came from, and because there's a mathematical reason for that, but that will be in our first example. Okay, so since we know that an inverse means that if I want to draw, or if I want to graph the inverse or plot the points, I have to switch the x and the y values, right? Well, in the same way, I'm going to switch my domain and range values. That means that my sine domain will now become my range. Okay, so my range now of my inverse function will now be from negative pi over 2 to pi over 2. And my domain will be the range of the sine. And so that will be from -1 to 1. And hopefully this isn't a stretch of the imagination at all. I mean, that should make sense, that if I have a point xy, the inverse of that is yx. So it should make sense that all the x values are now the y values, and all the y values are the x values. And so that's why I'm just going to switch them. Okay, and then down here, what I've written down are the coordinate points from negative pi over 2 to pi over 2. Okay, so what does the inverse sine graph look like? And I want to go ahead and show you down here. Okay, and check this out. Notice that these coordinate points are the exact same thing as we used up here for our sine curve. Notice what I changed. Okay, I changed the y and the x, right? Because that's how you find the x and the y coordinates. You just flip them. So the x went into the range values, and the y values went into the domain values right there. Okay, so if we look at the curve over here, okay, notice this. This coordinate point right here is -1. Again, this is x. -1, negative pi over 2. So I go over -1, down negative pi over 2. Notice how the x coordinate is no longer 0, pi over 2, pi, 2 pi. It's no longer the pi values. Again, the x and the y changed. The x coordinates, okay, it's gonna go from -1 to 1. So that's why this is the point -1, negative pi over 2. I'm just gonna kind of skip these two guys right here because they're decimals, but look right here. Negative pi over 6, -1. So negative pi over 6, -1. Or I'm sorry, -1/2. And so that's that right there. Okay? 0, 0 is right here. Pi over 6, 1/2. So pi over 6, 1/2. And then pi over 2, 1. Oh, I'm sorry, 1 pi over 2. Sorry, we're doing, these are the x coordinates. 1 pi over 2. So if I were to graph the sine curve on top of this here, remember the sine curve looks like this, right? So it would look like this. Go up, and it would go like that. And if I were to draw the line y equals x, as I said, it's always going to cut it right in half. And I know my graph's not exactly perfect, but as you can see here, it's going to be a reflection across the line y equals x. Okay, so in this chapter, it's actually not important that you know the graph. Okay, I'm not going to test you on knowing, do you know the graph, but what is important that we will be using over and over again is that you're going to need to know the domain and range of the inverse or the arc sine values. And I will demonstrate that in our first example.